When I first heard about this, I was like, I don't believe it. And I went out and did it myself. I bought $1,000 super zoom camera, tripod, went down to the
Hmm.
beach, set the camera up maybe 2 feet off the water. And it was a super cool, clear, calm day. It was like God delivered this perfect conditions to me. I
Hmm.
zoomed in on a buoy that was over 10 miles away. How much
Yeah.
curvature should it be at 10 miles? Do you know?
Mm.
66 feet. But I could see the buoy and I could see the surface of the water beyond the buoy. What does that tell you?
My guest today is David Weiss, known as Flat Earth Dave. Dave's a vocal advocate for the idea that the Earth is flat. As wild and crazy as that idea seems, I'm fascinated by why do people think like that? It's an interesting conversation. There's some brain teasers. It makes you think, but most of all, have polite discussions with other people that you might disagree with. So, on with the show. Here we go. A discussion with Dave often delves into concepts such as we live in a universe where Earth is a flat plane surrounded by the ice shores of the Antarctic, inconsistencies in NASA's narratives and the physics of space, and his personal experiments to show the Earth is flat. Welcome to my show, Dave.
Thanks, Daniel. Thanks for having me.
So,
Looking forward to the conversation.
to start, explain the flat Earth theory to those who've never heard the idea that Earth is flat and think it's the most ridiculous thing. Summarize what it is and your why you think it's so.
Yeah, if you Google flat Earth, Google is going to feed you exactly what they want you to see. They're going to send you a disk in space like this.
It occurred to me, well, it can't be literally flat because you can dig a hole. And there was a college kid that I was talking to about this, and he's like, well, yeah, that would mean it has to be a cylinder or a rectangle of some kind of box, even if it's a thin box. I'm like, you're a pretty smart kid. Yeah.
They're going to send you that. That is not flat Earth. That is it to make you laugh. This is flat Earth. Large bodies of water at rest need containment. A pond. Why does a pond exist or a lake? It exists because the land is higher than the water and it contains the water. So water needs containment.
Water doesn't need altitude to contain it. Water needs a force. Altitude and walls, the way Dave describes it, like it needs a wall to contain it, is not true. It needs a force. I think we're going to get to where Dave says he doesn't basically believe in gravity.
This is the shoreline of our word. That is Antarctica. Antarctica is not a continent at the bottom of a ball. It is the shoreline that surrounds our world pond. This is the average elevation of Antarctica. So Antarctica is the highest land on Earth.
Trying to get a model of this ice around us. What happens if you go past the ice?
That is a fantastic question. Now, before I answer that, and I'm happy to answer it because it's one of my favorite things to do, is we don't need to speculate what's beyond the shoreline of our world because it's all off limits.
I should have said, what happens when we get on the ice and we keep going? There's a National Geographic magazine that I saw the other day. It talks about 1914, Ernest Shackleton and his crew of 27 went on an expedition to reach Antarctica and be the first explorers to traverse it on foot. National Geographic shows the route of their 2-year ordeal, and it seems to actually, between it and the actual expeditions that have been searching for the Endurance, the ship, which they recently found almost 2 miles under the sea, it seems like they have pretty much traversed much of the Antarctica.
If you go south, 60 degrees south, no one's allowed to independently explore beyond there. So the question is, what is beyond 60 degrees south? That would be this pink line. And the answer is Antarctica, and who knows? So I'm gonna show you what could be out there. You're not allowed to explore here. You're
Yeah,
not
got
allowed
it.
to
Yeah,
independently explore.
totally familiar with that. You have to pay a lot for an expedition, and you can't get off
Yep.
the ship. And if you get off the ship, you have to take. They're going to babysit you. Tell me about your experiments to prove the Earth is flat. How do you get to the idea that it's not round?
Well, if the Earth has curvature, then it would have to have it would things would have to curve. For example, you can't see my mouth right now because it's behind physical curvature.
So, nope, I cannot see his mouth. There's a beach ball in front of it.
Right?
Mm-hmm.
Zooming in isn't going to help because there's physical curvature.
The ball does have curvature, but I think that's a compound sentence. I can't see him because there's a ball in front of his face. It could be a cardboard box, square, and I wouldn't be able to see his face.
Well, our horizon is not physical. It's an optical thing. So people say, well, we're so small, we're like a microbe on a basketball, it would appear flat. That's what we've been programmed to say. But here's an experiment we did using globe Earth math. Here's a canal or a lake, and we have a camera. It's on a frozen lake. Now, water at rest lies flat, testably, measurably, provably flat. Water, when it gets cold at rest, freezes flat.
So I'm going to draw a circle like the Earth. Pretend we have a glass of water that is a huge glass of water. It's a couple miles big, a couple miles wide, this glass of water. You fill it with water. The water is going to be straight relative to the tangent point on the Earth, kind of like a level. And Dave is assuming that in his situation with his experiment, his lake is such as this glass of water, but that's not true. His lake is part of the globe, has some curvature, and where it touches land, the land is containing it, but the water in between is actually, due to gravity, pulling the water down. At the sides, the water makes contact with the land, but in between, the water's following is part of the curvature of the Earth. So his lake experiment, he's actually performing on a curved Earth.
So we've done measure tests with lasers, with mirror flashes, with just sightings, and I'm going to show you one right now. These lights here are 8 miles, 7 miles, 6 miles, and 5 miles away. Now that doesn't sound far, but according to globe math, from a 6-inch observer height, this should be 30 feet below a physical curve.
So what Dave's basically saying is, if there's curvature and you're miles away, and something is miles away, because of the curvature, it should be technically at a, I'll say, lower altitude to keep it simple. Like it's around the corner, it's around the globe, so to speak. And you either shouldn't be able to see it at some point, or it should appear to be lower in the sky than it is. Light bends. It follows the curvature of the Earth, the gravity. Gravity bends it. Light reflects off something. As that light, the image you see comes to your eyes, the light is bending with the Earth due to gravity, such that when it arrives at your eyes, it appears as if it was straight in front of you. If it wasn't for that, everything might look goofy to us.
We're seeing them all on the same level, but on a globe, this one would have to be all the way down here, 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 and they'd all have to be refracting up to this line for me to be able to see them.
Here's a building. I'm going to draw the flat Earth idea, the way we see it and the way Dave believes that it is literally flat. You see light because it reflects off something. The idea that light follows the curvature of the Earth because it's bent due to gravity, and I'm going to exaggerate this curving of the Earth here. So say we have the building over here, and you're some distance away, miles away, such that there's curvature. Now, according to Dave, you wouldn't actually be able to see part of the building. What I'm saying is that light's still reflecting and bended due to gravity and follows the curvature of the Earth. So the same picture, the same light arrives at your eyes.
So here's a time lapse of Chicago from over 50 miles away. Now look, I'm holding my finger next to this building. It's not changing. This is over like 18, 20 hours time lapse. And this building is still right there. It's still right there. It's still right there. Now, it should be refracting up, down. It should be wobbling, but it's not. It's just staying right there, and it hasn't moved. Now, the top of this tower, the very top, should be hidden. So what we also did is on a clear day, our guys went down there on boats, put the Chicago in their lens, and then drove 50 miles across the lake on a boat and kept it there the whole time. If it was a mirage, it would disappear at some point, but it never disappeared.
An old-fashioned level works on the same principle as this glass of water. A level has a bubble in it, which will only stay in the middle of the level and the level is straight, such that at the point that the level is touching the object, in this case, we'll call it the Earth, it's straight. The yardstick is straight. The Earth is curved.
Here is this is the Knickerbein system, and you have these transmitters here. Now these are microwaves, and it is known that microwaves need line of sight, right? At the frequency that they're going off of, they can't theoretically bounce off the ionosphere because they would go right through it. So here it is. Here they are in Ringsted, 205 feet, and they were going to Mont Gramandi, but they were able to work. And the way that you know that they worked is they had one microwave going this way and one microwave going this way. This is a documented military experiment where they basically were guiding planes during the war down these microwave lines, because the plane, as it would be on the line, it would go, it would have beep, 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 beep. And when it has a solid tone, it's on the line. So the plane would follow this line, but it would know it's over the target when it comes across this other beam. Therefore, there is no curvature. When they were suggesting this, some of the scientists were like, well, it's not going to work because there's too much Earth curvature in the way. But the high admiral said, no, we're going to do it anyway. And they did it.
The ham radio operators I talked to, spoke to about this, who are experts in radio transmissions, they got really frustrated with me, not because of the flat Earth, but because, like, when you say microwaves, what frequency? The flat Earth argument and debate as to whether the Knickerbein system could have worked is based on that it operated at a microwave frequency. It did not operate at a microwave frequency, not even close. The Knickerbein system operated between 30 and 33 megahertz. For something to be considered a microwave, frequency actually must be 300 megahertz on the low end to 300 gigahertz on the high end. So the low end of what's considered microwave is still 10 times higher than what Dave is calling a microwave. I realized this as I was thinking about this more, and I recall that in the early days of cordless phones, the frequency of the cordless phones was 900 megahertz. That's 30 times higher than what Dave's calling a microwave. So if anything, these phones, if what Dave's saying is true, we should have needed line of sight to use these cordless phones, but that wasn't the case. The base station would be in the kitchen, and I could take my phone upstairs or even outside on the lawn and keep talking. I didn't need line of sight. It was the number 900 megahertz. I have some clients who are sensitive to electromagnetic fields, and they don't like the new cordless phones and the Wi-Fi. So if you're lucky at a Goodwill, you can find, and you actually have a landline, you can find some of these old phones that work at 900 megahertz. But why else didn't I realize this sooner? Because the slide in Dave's presentation has the title, Knickerbein Line of Sight. And during his presentation, as he's pointing, he's saying, these are microwave towers, and it's known that microwaves need line of sight. Whoever told him Knickerbein used microwaves was wrong. The scientists working on the system had doubts as to whether it would work. They weren't sure if the waves would follow the curvature of the Earth or not, how it worked. They did not have her make that statement based on saying it was a microwave frequency. It was simply at that time in history when radio, radar, and so forth was just being invented. They simply were not sure. It had nothing to do with the frequency, quote, being in the microwave range. And an incorrect association has been made in Dave's presentation between the phrase line of sight, and this results in those seeing that slide to assume that the Knickerbein system, in fact, operated at frequency in the microwave range. It was not a microwave frequency, not even close. These are radio frequencies. These are not microwave frequencies. And how do we get pulled into this discussion anyhow about trying to figure out how is it working when it says it shouldn't work? Look at Dave's slide here where I have it circled. To me, it looks like he's grabbed some pictures of dishes that may operate at microwave frequencies and cut and paste them onto the slide to make his presentation. That is not what the Knickerbein antennas look like. You can go online and Google what the antennas look like, and Knickerbein translates as bent leg. These are basically VHF antennas, long range VHF antennas. If you had a TV back in the day and you wanted to tune into, back in the day, you had to use a television, you had to use an antenna. It was, some of the stations were VHF. You had these rabbit ears you had to twist and bend to get the television station to come in. It's that kind of radio frequency. What to me in Dave's slide looks like when he's pointing to it and saying he's saying as a matter of fact, these were microwave antennas. They were not. They were VHF antennas. I'm sure he had good intentions. Somewhere he thought, I'm going to present this way because I think they're microwave. Someone told him they're microwave, so he goes and gets a picture of microwave dishes or something to cut and paste into a slide, to which the rest of us on quick thought maybe don't question that. And we start getting pulled into this discussion about, well, how did it work then if there were microwave frequencies? I call that disinformation, Dave. I call it an honest mistake, but I'm sure it led people down the wrong rabbit hole in trying to do the research. It's misinformation, kind of just like the...
And according to Globe Math, from this viewing spot, the top of Mount Canigou should be over a half a mile below the physical curve. Just like my mouth was hidden behind the ball, right? It should be behind the physical curve. You can say that curve is a house, a hill, whatever, a mountain, whatever you want, but it's behind it. You can't see it. At 175 miles, the light that's bouncing off of Mount Canigou isn't strong enough to push through all of that atmosphere, and it gets attenuated and it just becomes sky. However, the sun migrates 6 months into Cancer, 6 months out to Capricorn, but twice a year it lines up with the viewer and Mount Canigou. And when it does, it goes beyond Mount Canigou. I'll speed this up a little bit. And when it goes beyond it, the sun's light is powerful enough to push through, and it backlights the mountain.
To me, it looks like the sun has gone down and there's a little bit less haze, but you're starting to be able to make out the mountains.
The very top of the mountain here should be over a mile below the curvature, right? So the globe excuse for this is, I'll give you the globe excuse and I'll give you the flat earth excuse. The globe excuse is, well, the sun already set and the mountain is below the curvature, but the sun is refracting up, stopping at eye level.
That kind of supports the previous thing that I was suggesting, which is light follows the curvature of the earth from where the sun now is in the sky. If such that it is more powerful, then that would make sense why you can see it now, because it's like a stronger flashlight pushing through the dust and the haze.
From this viewing spot, Mount Canigou should be hidden below the earth curvature.
You can see the sun in the sky, even though technically it's supposed to be below the horizon.
Right. It's magically refracting up, but at the same time, the mountain, we're looking at the dark side of the mountain. That dark side of the mountain is refracting up and blocking the sun.
Like the beach. It's like the beach. The sun's going down the horizon, except there's a mountain on the horizon. You're looking out the ocean. There's a mountain instead of the ocean. Right. The sun's going down. We covered this already.
Let's talk about something that doesn't have to do with light. Then let's talk about something else. So here's an airplane. I'm showing I was on a flight the other day, and a pilot says we're going to be descending, and we're X distance from the airport. And I calculated if the plane's going 500 miles an hour, when they start descending, they're 125 miles from the airport. So when they start descending, the pilot has to calculate how many feet per minute he needs to drop to be able to get to the runway. It makes sense, right? If you're 100 miles away and you were 100 feet in the air, you have to drop 1 foot per mile to get to the runway, right? Just for an easy number. The pilot does this calculation and the plane will get to the runway. However, it's a flat earth calculation. At 125 miles out, he would be over 2 miles too high because the earth drops 2 miles in 125 miles. But they never calculate for that drop. They only calculate based on flat earth. So the flight data is measuring the distance of how much they need to drop to get to the runway based on a flat earth, and it works. If it wasn't, they'd be 2 miles too high.
What Dave is assuming here is that the distance used in the calculation from the pilot is based on literally a line of sight to the destination, which is not true. It's based on curvature. The distances on a map are based on curvature. Think about it this way. If you were to ask the highway people, I want to put a sign out that says 5 miles to this exit. They would drive from wherever you are on the highway to that exit to determine, oh, I've just drove 5 miles. The distance is actually based on the real distance, which is based on the curved earth. Airplanes also follow a curved path. As they go around the earth, they don't just skate off towards the moon. The airplane follows the curvature of the earth too as it's flying. When he says the airplane's 125 miles out, that 125-mile distance is calculated based on if you drove your car 125 miles. So we have 125 miles to go on the curve. Dave's imagining that the plane's coming in straight. It's going to be too high. The plane is actually following the curvature of the earth as it descends. It's dropping altitude, but as it does, it is following the curvature of the earth. Similar to how your car, you drive around, the street looks flat, but there's curvature, and you still know, I just drove 125 miles around the curve. It's the same thing with the airplane. I have a thought that I can explain this for you, Dave, but I can't do it in 10 seconds here. So as the plane is flying, there's a force of gravity pulling it down. And it's that force that has to be balanced with lift by the speed of the airplane enough such that it gets just enough lift on the wings to compensate against gravity to keep it at the altitude it wants to stay. So it's constantly fighting gravity to stay at a certain height. And that's what causes the curvature path. If you do it Dave's way, no, it is literally a straight line and there's no curved path. Then if you kept going, you would leave the planet. You would go higher and higher and higher and leave the planet. And that's something you can't do with the normal aircraft. They know the location on the planet, how far it is away.
Based on flat Earth measurements.
According to you, line of sight, or just
no, because it could be nighttime, it could be cloudy. They're above the clouds. Hold on. Let me answer your question.
Okay.
Right. All flight manuals say they treat the Earth as a flat, non-rotating plane for all of their calculations. They just treat it as a flat, non-rotating plane, even though it's not flat and it is rotating. But they do all their calculations based on a flat, non-rotating plane.
Well, that's perfect. I love it when things are simple and you can just go in the manual. And have you asked someone who wrote the book that you're speaking of on the aviation, how to fly the airplane, their thoughts on this?
No, but I speak to pilots from Qantas, Delta, American.
Perfect.
There's tons of pilots that are all very awake and aware of this.
And what do they have to say?
Earth is flat. They know it's flat.
My buddy's a pilot. He flies like the big planes to Russia and China, and he kind of disagrees. I'd be
ask him how he adjusts for curvature, because you know how planes maintain their level? They have a gyro. Right. So on the runway, they spin the gyro up. Everyone remembers playing with the gyro, and it spins up and it holds rigidity in space. It doesn't matter how the plane turns or up or down, left or right. It'll always be level to that runway. Let me run you through a thought experiment here.
Okay.
You know what the zero-G plane is?
No.
So it's a plane you can go on for a joyride. It does a parabolic arc.
Well, it's like if you have a bucket on a string or a tennis ball on a string and you're swinging it, there's that moment if you let go a little bit, the tennis ball will just float in the air. The string, you won't have tension on the string for a moment if you do it right.
So during the parabolic arc, you'll have a moment where it feels like you're weightless because you're in this container and it's falling at the same rate that you're falling. So you'll feel weightlessness, right?
Hold on. Sorry to slow things down. There's centripetal force and there's gravity. There's forces. So you got to describe it. What's the force on you at this moment?
That's what I'm trying to get to.
Okay.
So when it does this parabolic arc, you come out of your seat. Like if you go over a hill really fast, you come out in a car, you come out of your seat a little bit, right?
Mm-hmm.
Now, If you did that parabolic arc 10 times as fast, you'd get slammed to the ceiling. Agreed? If you're on a
Well,
merry-go-round and it went 10 times faster, you get thrown off the merry-go-round, right?
that's a perfect example because it's round and it's spinning. Yes, you would get thrown off unless you're holding on. So unless you hold on to the string of the tennis ball you're swinging, the tennis ball will fly out. Yeah.
And if you did the reverse of a upward parabolic arc, a downward arc, you'd get pressed into your seat, right? Fighter pilots have G forces when they take these turns, right?
Well, I'm thinking of the forces again. In physics, since you've been doing this a while, you probably understand free body diagrams and actually drawing force vectors on the object. That's how I think. And
I'm trying to get through a simple point. It should take
Okay.
1 minute, but it's going to take 40 minutes at this
Okay.
rate. Okay.
All right.
There are planes now, military planes that go 4,000 plus miles per hour. 4,000 miles per hour. The SR-72 goes over 4,000 miles an hour. I'm talking about G forces.
Yes,
right? Yeah, we can get into gravity. I'll explain to you what gravity is, but I don't think you're going to get it. I'm trying to get to a point where you just understand, like you didn't like things hiding behind curvature because they refract up.
I didn't say I didn't like it. I didn't say I didn't like it.
About how planes use a flat Earth measurement to calculate how much they should drop. And I'm going to explain to you, at a plane going 4,000 miles per hour, it would have to do a downward parabolic arc through free space at a mile per second, which is faster than free fall, right? A mile per second, or that plane will fly off into space. If the Earth is a ball going 4,000 miles per hour, it needs to nose down at a mile per second just to follow the curve of the Earth.
No, it doesn't.
Yes, it does.
You're still X number of feet above the Earth, wherever you are. Doesn't matter if it's flat or curved.
So if you're flying in a straight line through the air at 4,000 miles per hour, in 4,000 miles, the Earth is going to drop 6,000 miles. That the G forces, that would be a parabolic arc, and the pilot would get thrown to the ceiling. At 4,000 miles per hour, the G force would be like 160 Gs, which is just nothing can survive that.
This is our airplane, our tennis ball, and that I'm going to say gravity. Okay, even whatever it's straight down, right? The other force on you is straight. Literally, no, there's no nose up or nose down. These are the forces acting on the plane or this to try to break down. Okay, if there's a force on me, draw it on me, where it's pushing on me, how big or small it is, and then I can figure out what's going to happen to me relative to everything else, all the other forces on me. So if there's no other forces on me.
Here, look at this. This is the SR-72. It's going to go 6,000 miles this quarter way around the Earth.
Concorde is an example of a supersonic aircraft. It flew twice the speed of sound, over 1,300 miles per hour. Yet it was a luxury experience for its passengers who could afford it. Wouldn't happen if the G-forces were too extreme, making it an uncomfortable and horrible experience. The Concorde could fly at that high speed and cruise at an altitude 55,000 to 60,000 feet. Its passengers could see the Earth's curvature when they were at the maximum altitude, but passengers on the Concorde did not experience high G-forces. Why is that? Because of its design and, just as important, its flight profile. We want to go super fast, but we don't want to scare our passengers and have them exposed to a G-force that might hurt them. Then we design it. In the case of the Concorde, it took both two types of engines, and the wing is also very important. The reason that the Concorde lands at such a high angle of attack, its supersonic wings are thinner than normal airplanes' wings, which are thicker to provide lift. So when it's landing, it's got to stay in the air. It has to go at a huge angle of attack, like a bird coming into land. The plane was coming down at such a high angle of attack that the pilots wouldn't be able to see the runway. That's why the nose on the Concorde tilts. So also equally important with the Concorde, it prioritized a smooth acceleration. In other words, we're going to get to the speed really slow and a constant speed throughout the flight. So therefore, it has minimum changes in direction or altitude, which generate the G-forces compared to a fighter jet or high-performance aircraft. Going 4,000 miles per hour, to summarize, does not automatically mean a passenger would have to be exposed to a G-force that no human could tolerate. And this is why. It's because speed is not a factor. Speed is not a force. In physics, speed is velocity and the direction an object's traveling. There's no acceleration in that. The final speed of an object, we call it 4,000 miles per hour, is its initial velocity. We'll call it 0 for a plane at rest on landing before it takes off, plus its acceleration times the amount of time it has that acceleration applied. Many are familiar with the classic physical equation, even though they don't understand what it means. Force is equal to the mass of an object times its acceleration, F equals ma. Acceleration is equal to the force applied to something. No force, no acceleration. This has nothing to do with, I repeat, nothing to do with speed. Speed is not in the F equals ma equation. As soon as a force, the acceleration is no longer applied, in the absence of any other forces acting on an object, be it the plane, the object will continue to travel at that speed forever, indefinitely. This doesn't happen, of course, in real life. It doesn't happen with airplanes either, and that's because there are forces acting on the plane in addition to the thrust from the engine. If you cut the thrust, you still got drag, which is going to slow you down, and you got gravity, which is going to pull you down. But at a cruising speed, a passenger is not going to feel any G-force, as the pilot only needs to apply enough power to the engines to keep the plane balancing the forces of the drag and the gravity. Passengers only going to feel a difference in the G-force when the plane's accelerating, take off, and the moment you hear the pilot announce, if you're a passenger, no matter how fast your plane is going, if it's designed properly, you're only going to feel a G-force between when the plane takes off, accelerates, and when you hear the pilot announce on the intercom, we've now reached our cruising altitude. You may now feel free to move about the cabin. And then you're going to be allowed to move about the cabin, use the lavatory, and so forth, until the captain announces that you should take your seats, either because of turbulence or landing. So turbulence is a new force acting on the plane that has to be balanced out by some reaction by the pilot, which is going to cause a momentary change in the force on the plane and the passengers. Passengers on the Concorde only experienced an increased G-force, takeoff and landing. And those forces, here's the incredible thing, were still considered minimal compared to the other aircraft due to the design of the Concorde. Its wings and engine and flight profile were designed to provide a gradual, I repeat, gradual acceleration and controlled descent. So imagine you're pushing someone on a swing or a merry-go-round. You could apply sudden and large force to get them moving super fast, super quick. Maybe you might need the help of your friends to do this. Or you could get them going up to the same speed if you gradually, slowly push on the merry-go-round or the swing and gradually increase keep giving them a little push on the swing or the merry-go-round. You could get them going as fast as if you applied a sudden large force. So when we get in discussions like this, it's best to go, okay, draw me the free body diagram, which is a picture of the object by itself. By itself, you then draw the forces acting on it, because if there's no force, there can be no acceleration and no change in its velocity. The pilot will use the flaps and other controls on the plane and change the thrust on the engine and change the angle of attack or the power to maintain a given altitude and speed. And this is an example of why you can go supersonic speeds, have a luxury experience. It doesn't mean it's impossible. You won't be able to tolerate the G-forces. Okay.
No, you think that's straight. You think that this is straight, right? You think that this path is straight.
I think the
is
picture.
Is this a straight path? Yes or no? I'm drawing my hand around the globe. Is that a straight path?
He's got.
I'm holding a globe and I'm drawing my fan. I'm just staying an inch off the globe and I'm going around the globe. Is that a straight path or a curved path?
When you do the force diagrams, there's no expression with words and thoughts or I think this thing. You just do the math on the forces. You draw an object, You draw the forces acting on it, and it's that simple.
So why don't we feel the motions of the earth?
I didn't say feel, I said forces. And to answer
Why
your
don't we
question,
feel the forces of the motions of the earth? Do you know what the motions of the earth are? How many different directions is the earth moving at once?
I'm trying to answer your question.
I'm trying to I'm
This
trying to
is
get you to understand.
so then draw me a free body diagram. Draw me the
A three
forces,
a, a three body diagram.
because that's how we do it in science and physics. We think about it and I'm like, draw the picture of the forces
You,
on me.
you know what the three body problem is?
What's the three body to start
You,
with?
you,
What is three body?
any three gravitational bodies. You know the problem, the three body
I
problem. Do you
do
know what
not
it is?
know this three.
All
I
right,
didn't
so
know it was
we've
a
got
problem.
we've got so many different things lined up here. So let's just go. We'll go to that.
Let's just agree that Daniel needs more time to analyze stuff, to talk intelligently. And
Right.
let's move on to what I really am also curious on. Let's pretend the Earth is flat.
I'd like
Okay.
to I'd like to address though one thing you said before. You said
Okay.
you were talking about satellites, right? Who that you were involved with satellites or somebody was? This is a satellite being launched from the space shuttle. Do you believe that the space shuttle launched satellites?
The space shuttle launched satellites. Do I
They
believe?
carry satellites to space,
Um,
and then if I show you them faking a satellite launch,
uh,
will that make you wonder?
I think this is going to get into is that it's all a lie, that they don't launch any satellites.
This is the launching of a satellite from NASA, from the space shuttle. And as it launches off, and when a camera pans up,
So Dave,
you can hold on. You can
well,
see the wire.
for
You can see the
listeners,
wire. Hold on. I'm pointing. There's a wire lifting this thing up. There's a wire right here.
I don't see a wire. This quote wire almost looks like a little plume of, it's not smoke. It's too sharp to be smoke, too thick to be a wire, grainy. It's a very grainy image.
Pulling this thing up. You can tell that it's been lifting up by a crane, and there's a cable on it. This is the model, and that satellite launches aren't real.
Even if this is a doctored photo, doctoring a photo or getting a doctored photo of a space shuttle releasing a satellite does not mean the Earth is flat. Well, why would they make a photo like that? Or, well, who's they? Did NASA give you that photo? Where'd you get it? That's a great question, but it doesn't mean the Earth is flat. The doctored photo is only inspiring you to think and to question everything, which is great and wonderful. We're trying to raise money to get more money for our program, the satellite program. I'm just making this up on the fly, but everything's possible. The actual photos we had weren't great, and we need to take this to Congress. We need to show some real impressive photographs. So it's the same thing in the end. We just created it artificially, but it is what's happening. I'm just going to say I agree it's fake. Just to move on and
Sure. Where do you want to go now? Everything they tell us, everything they've taught us about space is fake because space is fake. There is curvature. You can't have high pressure next to no pressure without a container.
Yeah. When Dave said you can't have pressure next to no pressure without a container, I think what he means, imagine the Earth and there's pressure, there's air pressure outside, right? There's a pressure outside, the air, the atmosphere. Space has no pressure, meaning Dave said you can't have pressure with like the atmosphere with no pressure space without a container, meaning a lid over the flat Earth. But that's again not drawing the it's called FREE body diagram in physics. If you had pressurized the atmosphere and there was space, all the atmosphere would have to leak out, except you have gravity. Earth is flat. What do we do if the Earth is flat?
Good question. The solution is, our thoughts create our reality. And what they're doing is they're controlling our thoughts. They're hiding the fact that we are at the center of creation. They're hiding that we have great power. They're hiding that there's probably more land, more resources. They're hiding free energy technology. When you wake up to the flat Earth, it unlocks you from the prison, right? Because the globe is a prison for your mind. Okay?
What's the solution, Dave? What's the solution?
The solution is to unplug from the system, to realize that we are important, that we are special, that we have great power, to realize that our thoughts create our reality.
The most important thing is not to get angry about it. That's not going to solve the problem. Being aware of things is very helpful. That's the first
Well,
step. You have
our
a problem.
community, we have there's over 200,000 people on my app, and all of them are awake and aware that.
I don't think people getting crazy and angry is the solution either.
Well, the Globers are the ones that get super angry.
Like Globers, I think he's referring to the people that believe the earth is curved. My colleagues and friends that I've mentioned it to, they didn't get crazy or angry at all. They didn't insult him like Dave's group insulted me on Dave's YouTube channel. In the long term, I think you need to be kind and respect each other's opinions is the best thing, right, Dave?
I got you. My point is, you're not going to learn about flat Earth in 1 hour.
And I wonder now if Dave's been attacked. He probably has. And that's as unfortunate. And then I get why his group has kind of been disrespectful to me. Question everything. Do not believe what you're told, period.
Sure.
And then you will have no friends except like me and Dave are friends now because we can agree to disagree. And that's fine, right?
Yeah, all good.
And I still need time to go over your flat earth. It's fascinating. That's why I had you on the show. Thanks for being on the show, Dave. I really appreciate it. Thanks for being patient with me. Patient with me. Thank you. Have a good
Thanks,
day.
brother. See ya.
I did have to think about it. It's a win-win for me. It made me think. Einstein, by the way, he couldn't do the math. He had these ideas. He couldn't do the math. He needed a colleague to do the math for him to do the equations for some of the stuff. He had the concepts. That's what's the most important thing, the concepts. We all do this. You make assumptions. Why would somebody do that? Part of what's keeping us from society and individually from moving forward in our lives, we're making these assumptions. Even if it's true, yes, Earth is flat. Why did they, quote, lie to us? You don't know that everything doesn't have a positive intention also. As fun as it was to have this kind of open-minded conversation, you can travel from any point you are in the globe, go east or west, and completely go around the globe back to your starting point. You can fly or take a boat, follow the oceans, either direction, east or west, from wherever you live. So, of course, the Earth would have to be at least a cylinder. I would, if you asked me, I would tell you I would tend to believe the Earth is round. And you can count me up to one that's not going to be disrespectful to him for having his own beliefs and ideas. He'll be wrong from here on out when he classifies all of us globers as being hateful and angry at him, because I'm not one of them. The end intention of Dave, though, is very admirable. This awaken idea to question everything. I would encourage him to get his listeners to understand it's not helpful to take the attacks from, quote, globers personally either. Think for yourself, question everything, but don't be angry. The Beatles had it right when all we need is love and understanding. We need to work together on making the world a better place. Thanks for listening to my show. I'm Daniel. Take care.